Okay, we can get started. Today, Nicoletta is away, so I will be introducing the speaker. I'm Valentina Staneva, and I'm a data scientist at the eScience Institute. And today we will hear from Dongfang Zhao, and he's an assistant professor at University of Washington and Tacoma, and both affiliated with Seattle campus and the eScience Institute. His research interests span many different topics: databases, cryptography, high-performance computing, and artificial intelligence. Before joining UW, he was a member of UC Davis, and before that, he was here again at the University of Washington at the eScience Institute, and that's when I first met him. So he liked it, so he came back. And we're excited to hear today his work on enhancing performance in database encryption and recent developments in vector databases. So,
all right. Thank you, Valentina, for the introduction. So like Valentina said, I was here before, so this is not very new for me. So in today's talk, I will focus on two topics, but mostly on the first one. So if we do have time left before, I think 5:20, I've tried to cover a little bit on the recent developments in vector databases. So, but the focus of today's talk will be on the first one, database encryption. So another slide about myself. So I was here before. I was affiliated with the Allen School and the eScience Institute. So just FYI, the CSE was not called Allen School before in 2016 or 17, but then they just upgraded the department into a school, I think in roughly 2017 after I left. So so I worked with multiple researchers at UW. So Magda was my advisor at the CSE, and Ariel was my advisor at eScience. So so Magda now is the director of the whole school, of the Allen School. And then I moved to Nevada and California. So I kind of drove back and forth between Reno and Davis because I was based in Sacramento area. So, and then last year I came back, taking an offer at UW Tacoma. So that's another satellite campus, like 30 minutes drive from here. Of course, I just regained the affiliation with eScience and the Allen School. Unsurprisingly. Okay, so for today's talk, like I said, there will be two main parts or topics. So the first one will roughly introduce some of the most recent advances in both databases and encryption. So I was working on the overlap or the intersection between both cryptography and the database systems. And as a usual technical talk, and the first part is broken down into a few sections. Right? So starting from the background, and then articulate the problem, and then I will introduce the proposed approach, followed by some evaluation results, and eventually pointing out some of the future directions. So, and if we have time, then I will also talk about the second one, which is about the vector database. It's of great interest partially because of the popularity of large language models. Right? So, so if you have heard of, I believe I've heard of large language models, but there's one of very popular applications built upon LLMs or large language models, which is called the RAG, so the retrieval-augmented generation. So the key idea is to combine both the local database information and the general model trained by OpenAI, for example. So, and the VectorDB basically is an indexing mechanism to help you or to help the users to accelerate the information retrieval from the local database, so that the query results from the large language model can be, for example, faster or more accurate. So, so that's a very quick overview of this talk. So let's start with the first part. So, and also feel free to stop me if you have any questions. So, all right, so let me give you some background of this first topic or direction, right? So as the name suggests, it's the intersection between cryptography and the database. So, but this intersection is under a specific context or scenario. So in other words, we are working on a very specific scenario of databases where we assume the database is not being managed locally. So in other words, it's called the outsourced database. So it's like you are using, or maybe you're managing your file or maybe your data using AWS or Google Cloud, right? So this is getting more and more popular. But before that, let's get to the more fundamental definition. So some of which may already be familiar with you guys, but I still want to reemphasize this subtle distinction between a database and a database software, basically. So technically, a database is just a collection of files. So you can think of a database as some collection of data, maybe on your local disk drive, or maybe on some remote cloud drive. So, but the key word here is that it's all about data, right? But here we are so we are trying to make a distinction between a database and a DBMS, right, which is the acronym for Database Management System. So, so if you have taken any database class from the Allen School now, maybe not only the Allen School, but also maybe the iSchool. So, this might be some sort of review for you, right? So a DBMS is not only the database, right? It's more about the software to help the users to manage their data, right? Regardless of where the data is located, maybe local disk drive, maybe in a remote cloud. Right? So, but sometimes people just abuse this terminology. Sometimes people use database to refer or to mean the software to metadata. So, so in this talk, I may or may not make a clear distinction between DBMS and the database. So, but feel free to stop me if that's confusing. So, and a not outsourced database, probably you have imagined what that means, right? So it just means the database or the database software, usually both, are managed by some third-party vendors or provider, right? So like Amazon Web Services, Google Cloud, Microsoft Azure, right? So I think many of you may have used those services already. So, but still, I try to give a somewhat formal definition of what we mean by a not sourced database. So it's either the database itself or the software is being outsourced, right? Or both. So, and also list some popular public cloud services. So, so if it's not obvious to you, then I can just quickly try to convince you why this is useful, right? So usually it's cheaper, to use the outsourced database service than buying the license of a specific database service software and then install it on your local drive. So, and sometimes it's not only cheaper, it's also faster, more reliable. So, so that's one of the main reasons why, this, I think they call it paradigm. Right? So, it's getting more and more popular. So, cheaper, faster, and it's also supposed to be easier. So you don't have to install it on your local disk drive. Right? So just usually sign on a service and then maybe enter your credit card information and then you can start using the service. But it's not perfect, as you can imagine. Otherwise, I will not talk about it. So there are multiple limitations, but today we will focus on the security part of outsourced databases. So, so I think one of the key questions we want to clarify or maybe want to answer is that, do we really trust these third-party providers, like let's say Google, Microsoft, to manage our data? So it could be yes or no, right? So it depends on what kind of data you're trying to outsource to the remote cloud service. So, so if it's just maybe your past picture, then maybe it's fine. But if it's about your, I don't know, healthcare information, you might be hesitant to share your data with Google or Amazon. So, then the question becomes, if, let's assume, you do not fully trust those third-party providers. So how can we still leverage this supposedly cheaper, faster, and easier to use cloud-based database service, right? So one of the most straightforward solution is to encrypt your data. Right? So you can just encrypt your healthcare information, right, before you upload the data, the encrypted data, right, to Google or Amazon, right? But does that really work? Well, it will work in the sense that the data itself is now much harder for the third-party provider to pick at, right? So it's really hard for them to decrypt your data without the key that you should keep secret, right? But there's another issue if you do this encryption and then uploading paradigm, right? Because once you encrypt your data and then upload to the Google Cloud, for example, then you are losing the capability of doing queries over those encrypted data on the cloud. Right? So I think I should click a few more things, right? So let's say you are an owner, right? You're the owner of some small business, right? And then you're storing the employees' salary information, and then you encrypt them, and then you outsource those encrypted data to, let's say, AWS, right? But then at some point, right, maybe the IRS, right, wants to check the average pay rate of your company. Right? So then what we can do? Well, the best you can do is to download the encrypted data from AWS, and then you decrypt them, and then you do this. So by the way, this is very simple SQL query. So if you have not taken any database class, you can just think of this first query as a function to return the average of a set of values, right? But now the values are not plain text values, so they look like random strings. Then the question is, what if we do not want our users not to download the encrypted data to the local disk drive, right? But still being able to retrieve the average salary from the encrypted data sets on the cloud. So in other words, we want to do some meaningful computation over those encrypted data, right? So that's really one of the fundamental questions in cryptography, not only in database, but the database is, I think it's a very strong use case of this cryptographic paradigm. All right, so I think I have another example to illustrate this practicality of this application or this paradigm. So maybe we want to return the employees' names who are making more than, I think this is 90,000 per year. But again, remember all of this salary information are already encrypted, so they look like random strings. So you cannot, well, the database itself or Amazon cannot really simply return or calculate this comparison between those encrypted salary numbers and 90,000, for example, because they are just random strings. Okay, right, I think that's just another explanation. So, so the real question or the fundamental question we try to answer in this direction of research is that how can we make this sort of outsourced queries meaningful and practical? So again, so the challenge here is that we cannot simply compare or make sense of those encrypted numbers on the remote cloud services or databases. So, so on the one hand, you have your data encrypted perfectly, well, not perfectly, but mostly secure, but then you lose the capability of doing some meaningful computation over the data, right? And that also touches on another fundamental concept of DBMS. So a database management system is not only about storing data, right? It's also about querying your data, right? So if all you need is to store your data secretly, then you do not need a database. You do not need a secret database. You only need a secure storage, like an outsourced hard disk drive, not necessarily a database. So one of the reasons why we want to use this database service is to allow the users to do some meaningful queries over the outsourced data, right? But now we are seeing that if you want to keep your data secure, then you are losing that ability, right? That ability. So how can we solve this? So, but before that, I think I added this comment yesterday. So, so there's another research direction, which is orthogonal to the stuff that we are talking about. So, in some scenarios, we do not want to reveal, or we do not want to expose what kind of queries we are trying to make over the data. It doesn't matter whether the data itself is encrypted or not. So we do not want to expose our query. So think about some private query you try to make, you do not want others to know, right? But here we are assuming our queries are not sensitive. So the query itself is plain text. So, but if you are interested in this private query stuff, I think it's called the private information retrieval, PIR. But again, that's orthogonal to today's talk, or to this outsourced database. Right, so it's called PIR, so you can Google it if you are interested in that direction. So, okay, so if you think about this problem, it's not that, I mean, it's not that hard to encounter such problems in practice. So that's why we do have multiple candidate solutions to this problem. So in other words, we do have a few not perfect, but functional, I would say functional. I didn't say useful because they're not quite practical yet. So they're functional. So types of solutions. So I will list, I think, two of them before we go to the core of today's technique. So the first one is called differential privacy. Some of you may have already heard of this. So the key idea is pretty straightforward, but the formal introduction is not as simple as this. But I would like to share with you guys the very key idea using non-technical terms. So what do we mean by differential privacy? So we assume our data set consists of multiple values. So differential privacy allows us to keep some statistical information of our data set. So let me give you an example. So let's say you have a vector, right? So the original data has 4 values, 1, 2, 3, 4. Right? So we can add some noises to each of the 4 values of the vector, right? So in this case, I'm trying to make the overall, the overall noise to be able to cancel out. So basically, we just add the 0.1 to the first one and then subtract it from the second one. And then I do the same thing, but this time with the 0.3 to the third and the fourth numbers. So overall, this vector is still maintaining the average value, right? Of course, not the variance, of course. But this technique is enough for those kind of queries, for example, to return the average number of your data set. Right? So you can assume that there are maybe four employee salary numbers, right? So now you are hiding the individual employee salary, right? But still, you can return accurate average salary number from your employees, right? So you're not revealing or you're not exposing the individual employees' salary number, right? But still, of course, it's much more complicated in the formal definition or in the formal usage of differential privacy, but this is hopefully sensible to you guys. But as you can see, before that, so I think it's just I reiterate the example I just used. Right, so there are some limitations of this differential privacy method. So if you think about it, if you simply convert your data set into these 4 values, then what if in some other queries, we do want to return an individual employee's salary? So you cannot do that since easily, right? So, so in other words, there's no deterministic function for us to convert, for example, the first number 1.1 back to 1.0. So, so differential privacy is more for maintaining the invariant of some statistical information, not the individual piece of information. So, and also maybe, so I think let's give another example here, right? So if we simply want to return the highest salary from our employees, then this approach will not work, because again, So the fundamental reason is that, this DP or different privacy is not supposed to be used for acquiring individual data, right? Because if you try to return the highest number from the data set, right, it's possible that for example, the third one, right? Maybe I add 2.0 to the third one, to the third value, right? Which will make 3.0 to 5.0, right? And then maybe I just subtract 2.0 from 4.0. Then the third element will become the highest salary number, right? So it will not work. Well, it will not always work. Right? So, okay, so that's the first one. I mean, the first approach, which is called differential privacy, is very popular, especially in the community of statistics. So because it's more like a statistical approach rather than a cryptographic approach. So, so it's all about distribution and the noise canceling. Right. So the second one is called a secure multi-party computation. So this is more leaning towards the cryptographic part. So, so as the name suggests, we are assuming here multiple parties or multiple servers exist in our application, right? So somehow, so the simplest case is that we have two servers, right? So we have two database servers. But here's one, personally, I think a very strong assumption here. So those multiple servers are not supposed to talk to each other, or at least not to collaborate or to collude together to do something bad. So this is also one of the main reasons why this. So it's also called MPC in the literature. It has not yet widely been deployed in practice in production systems, because, well, mostly because of this strong assumption. So so if you want to apply any this MPC approach, then you need to make sure the servers do not collude, right, or do not work together, right, to try to compromise or to attack on the outsourced data or system. So, so I think I'm also giving another simple example here. So let's assume there are two servers, DB1, DB2, two database servers, right? So, and let's say our original data has two simple data points, 88 and 99, right? So one of the simplest schemes, right, in MPC is to split one piece of data into multiple shares. They call it shares. So then in this case, I think I'm also using very simple technique, right? So not technique, it's arithmetic, right? I just split each of the two numbers randomly, right? So that we have two databases, and each of which stores only a partial information of the original data points, right? So 33 plus 55 is equal to 88. Right? So now if you look at one single database only, then you cannot really infer the original data information, right? I mean, if you're lucky, you can, but it's you cannot really make reasonable guess, right? From, let's say, 33 to 88. It's completely random. So, and if you think about this approach, right, you can still do some meaningful queries, right? For example, you can still do average, right? Because we did this splitting using the simple subtraction, right? Of course, you can add them back and then do the average, right? Because addition is associative, and also commutative. So, right, so it's going to be the same. So, but like I said, this approach is not well, at least has not been widely used in practice, because you need to make sure in this example, DB1, DB2 do not collude, right? And if you think about it, this is really hard. It's really a very strong assumption, right? So it's like I don't know. It's like the people's trust. It could not be the case. So right, and another less critical issue is about the system itself, right? So if we simply outsource, or if we simply split the number or the values into different, let's say maybe one for Amazon, one for Google, but then we are increasing the workload of our users, right? Because the user is responsible for aggregating the values together, right, at the final stage of the application. So, well, the user may or may not have the resource to do this aggregation, right? Because, well, we are seeing a very simple example, right? But in practice, what if, let's say, I have a billion of numbers, right? So then, are we gonna ask, well, not only, so there could be hundreds of servers, right? So then the user will have to collect 100 individual pieces of information and then do the aggregation, right? And the aggregation may not be simple addition. It could be some other statistical, sophisticated calculation over those potentially large number of shares from different servers, right? And the third one is actually our today's focus. It's called homomorphic encryption. So as you can imagine, we are trying, well, not we are trying, so this one bypasses some of the limitations of the first two approaches. So, for example, it does not, depending on the statistical information of your data sets. So in other words, we can still decrypt the encrypted data stored on the outsourced database. Right? So that overcomes the first DP's limitation. And so homomorphic encryption is also supposed to be working on a single node. So you do not need to have multiple servers, right, with the strong assumption that they are not colluding. Right? So let's take a look at this homomorphic encryption. Right? So I just want to highlight the advantages of this third. I think this is the third approach, right? So it can work well on a single plain text message, right, and also on a single server, right? So homomorphism is actually a term that we borrow from mathematics. So it basically means we're supposing there are two spaces, that's some kind of abstract spaces. One is for the plain text messages, and the other one is for the ciphertext messages. So somehow we want to have this function or map from the plain text space to the ciphertext space, such that the well-defined function, which is called addition, is maintaining the algebraic structure over the plain text space. I know it sounds a little complicated, but it's very simple. Maybe let's look at this example, right? So let's say if we have a negative homomorphic encryption function, right? So that means, so I think I should have first introduced this term here. So HE means homomorphic encryption, right? So let's assume that we have applied encryption schemes to both A and B. So A and B here denotes the plain text values, right? So maybe 1 to 2. So this additive homomorphic encryption scheme allows us to do the addition directly between two ciphertext messages. Of course, usually in practice, this plus sign is not the regular plus sign that you use between integers. So it's usually defined as a function, maybe called addition or maybe called something else, but semantically, it's just the addition between two ciphertext messages, usually two random strings, with one single important property, which is here, right? Because the output of that addition function in the ciphertext space can be decrypted back to the correct addition between the two plain text values. So I'll just pause here for maybe a few seconds here to make sure you understand this simple equation. So HEA here represents the ciphertext message of A. A is a plain text message, right? So you see why this is, in some sense, more or is preferred, right, over the MPC and differential privacy, right? Because you do not need to rely on the assumption of non-colluding requirement between multiple parties, between multiple servers. Also, you can still recover. I didn't say it here. So you can simply also cross off one of the two values here. So you can still decrypt a ciphertext message back to the correct plaintext message here. But this is even stronger. So you can not only decrypt a ciphertext message one by one, you can also do that over the addition between two ciphertext messages, right? So so that sounds a little magical, but so it's just involving some algebraic arrangement and rewritten. So so here and usually when we talk about homomorphic encryption, we care about two operations: addition and multiplication. So so a multiplicative homomorphic encryption is similarly defined. So we are able to decrypt the multiplication of two ciphertext messages back to the correct value that is the product of two plaintext messages, right? So here I use this this red or I think orange color to emphasize that those values are not supposed to be decrypted on the server end, right? So in other words, for Amazon or for Google, they can only see two random strings, but they can do this addition between those two random strings for the user, right? And then the server or Google or Amazon can send back the result of HEA plus HEB back to the user, right? So the user, well, the user still needs to do the decryption, right? But the user does not need to download potentially large number of individual ciphertext messages, right? So in other words, the user does not need to know or does not need to download HEA and HEB. So they only need to do this once, which is the decryption of some algebraic results of individual ciphertext messages, right? Right, and if the scheme, if the algorithm supports both addition and multiplication at the same time, then we call this scheme as fully homomorphic encryption. So, if you do not have a deep mathematical background, then you may wonder, why do we so care about multiplication and addition? Because basically most of our calculations are based on these two fundamental operations. So you can define division if it's a field, or you can define subtraction if it's a group. But usually with plus and multiplication, then we can, so basically you can build a polynomial, right? So a polynomial can be used to approximate many functions, right? Using the, I think it's called power series, right? Or the Taylor expansion, things like that. All right, so I think just talk about that. However, so far all sounds good, right? So it can allow us to do addition and multiplication on the ciphertext space, right? So what is not good, right? So we want to be, objective about this this third approach. It's not a perfect solution. So first, it's slow. So it's much slower than differential privacy, and I think it's also slower than MPC. So if the MPC system has a reasonably fast network connection. So why? Because we need to keep sort of algebraic invariant between these two algebraic spaces, right? One for the plaintext, the other one for the ciphertext. Right. So, and if you think about this homomorphic operation, so for example here, right? So we are really talking about three types of operation. The first is the encryption itself, which is HE parentheses, right? And then you can add up two or maybe more ciphertext messages, right? And then the third one is about multiplication. So then when we try to understand the performance of homomorphic encryption, there are actually three most important performance overheads, right? The encryption itself, the addition and the multiplication. Of course, you can argue, the decryption also takes time, but usually, if you think about the reason why we want to use homomorphic encryption, well, one reason is to try to avoid decryption multiple times. So we try to do the decryption only one time, right, at the end user. So usually we do not we are not that concerned about this decryption because that's usually done once, and that's usually faster than encryption. So okay, so like I said, so this is very slow. Then we want to understand which part is the slowest part. So for database applications, arguably, the encryption is probably the worst part because usually when we are trying to deal with a large volume of data, so usually the encryption itself is the bottleneck of the whole system. So so I think what's following is one recent optimization technique that we published last year in the database conference. So we try to accelerate this encryption procedure in the context of applying homomorphic encryption to outsourced databases. So so like I said here, so it's very slow. I know very is not an accurate word. So it's very slow in terms of the running time in the context of outsourced databases. So so let's try to articulate this problem. So we try to accelerate the homomorphic encryption or the speed. Supposing there is a large volume of data being outsourced to some third-party cloud providers, Amazon, Google. So how can we do that, right? But before that, so let's maybe clarify some of the design goals. So I think this is also a general rule for many other fields or for many other areas in computer science. So before you start designing something, you want to make sure you have a super clear requirement or a list of requirements, right? So let's temporarily give a name for this new, supposedly faster homomorphic algorithm. Let's call it ACC, HE, ACE, I think in the paper we call it something else, but then let's just use ACE, HE for now. So of course, the bottom line is it should maintain the correctness. So in other words, it should be able to recover the correct addition or multiplication after decrypting the homomorphic addition or homomorphic multiplication of two ciphertext messages. Right? That's pretty obvious. Otherwise, the database is not useful, no matter how fast this is, right? So it should be correct. So, and so the second one is about security, right? That's also one of the hard requirements of this paradigm, right? Because if it's not secure, then again, it's not very useful. Right? So correctness, security, right? And then, based on these two hard requirements, then we want to accelerate the speed of this encryption in this context. Right? So, and there are some more technical details about how we can show that this is secure, right? Because secure, again, this is a somewhat subjective word, right? So what do we mean by secure? And if you have not taken any security class, this might still sound a little vague for you, right? So what do we mean by secure? Do we mean that, for example, you cannot recover any individual values? Then do you think your database is secure? Or yeah, maybe. So, but there's a very rigorous definition in security regarding the security of a system. So usually it means that the attacker cannot review anything about your data, not only about individual data, but also some statistical data, including average, right? So in that sense, that means, for example, I think the simple example I showed earlier, using that different privacy, like adding 0.1 and then subtract 0.1, right, on the first and second elements. So that one is not considered as secure from the perspective of computer scientists, because you can still, well, the attacker can still recover the average of your data set. Although they cannot recover the individual employee salaries, but being able to recover the average of the data sets is still considered as insecure, right? But that's a little off the topic. So I just want to make sure that, so at least technically, our research goal is to make sure, or one of the research goals is to make sure the accelerated homomorphic encryption scheme or algorithm is still secure. And when we say secure, we mean secure in the sense of computer science, right? Not the common sense. So, but since this is not a secret class, I will not talk too much detail about that. Right. Okay, so far, all of the stuff I have talked about was actually not new. So there exist some popular homomorphic encryption, right? So remember I mentioned the additive or multiplicative and also fully homomorphic encryption. So so let's maybe take a look at how slow they are, right? But keep in mind the goal of this research is to accelerate the speed, right? So but now I'm showing how slow the existing methods are in the context of outsourced databases, right? So we tested one of the actually one of the fastest additive homomorphic encryption schemes, which was called Paler or Piler. It's a French name. I'm not sure. So and we deployed this encryption scheme on a very popular distributed database, which is called Cassandra. So so roughly speaking, our experiments showed that the slowdown was about or on the order of between 5 or 15 times slowdown. So in other words, if without any encryption, if it takes 1 second to upload your data, then now it takes like 5 or 15 seconds. So so this is a huge performance gap here between. Of course, it's insecure if you simply upload your data in plain text format, right? But you see the big performance gap here, right? And I think the figure also shows the gap for different data sets. Right? I think we picked the 3 popular data sets: COVID-19 data, Bitcoin. But I don't think we need to read too much about the figure. So just maybe keep in mind. So roughly speaking, applying this homomorphic encryption or one of the fastest homomorphic encryption schemes in the real world will slow down your system by roughly 10 times. So then it's a big decision to make whether you want to make your system more secure than by sacrificing your performance by tenfold. Right? Is it worth it? I don't know. So but our goal here is to shorten this gap, right? So while maintaining the security. So so our goal here, let me see. So one of the straightforward optimization that we can think of is to leverage multiple cores, right? But if you think about it, so these multiple cores are applicable to both encryption schemes and additions. So so we want to find something more fundamental here. So by that, I mean, if you can parallel the encryption of for your local data, then you can also parallelize the uploading speed, right? So supposedly the network bandwidth is not the bottleneck. Right? So so simply applying multiple cores for the encryption is not a fundamental advancement, right? In this context. So let me see. So then how can we come up with a more fundamental approach to accelerate this encryption, right? So let me see whether this, right. So we did some profiling of this homomorphic encryption and addition. Right? Remember, addition is one of the 2 fundamental algebraic operations in both the plain text space and the ciphertext space, right? So if you look at this figure, and you can ignore those right columns, right? So sorry. So see the time here for encryption if we only work with a single core, right? So it's about 2 times of magnitude slower than the addition between 2 ciphertext messages, right? So in other words, I forgot which data we used to get this data to get this figure, but you see the huge gap here, right? And the y-axis is in terms of a logarithm scale, right? So it's not simple like 2 or 3 times. So it's actually 20 times, or actually 100 times, right? It's 10 to the power 2. Right? So in other words, it's and this is also aligned with what I said before. So the encryption itself is much slower than the addition. And I have not talked about the multiplication, right, because it's even more complicated. Then the idea is, how can we somehow offload the expensive encryption operation to start of addition, right? Because addition is like 100 times faster than encryption, right? According to our profiling here. So in other words, well, not in other words. So then it's not that hard to think of this idea. So how about we pre-compute the encryption of some numbers? Right? Then when we are asked to encrypt another number, then we simply add up those pre-computed ciphertext messages. So in other words, we do not from scratch encrypt a new number. So instead, we just apply the addition function over those pre-computed ciphertext messages. Why? Because this is like 100 times faster than the simple encryption from scratch. Right? So as long as we do not add up, let's say 100 or maybe more ciphertext messages together, then it should be faster than simply encrypting a new number from scratch, right? According to this data, right? Sorry, right? And that's what I mean by this statement here. So we're going to pre-compute some encryption of values, right? So if you have a CS background, then it's probably not hard to think of some candidate values you want to pre-compute, right? 1, 2, 4, 8, 16, etc. But actually, you can pre-compute anything. So so in the extreme case, you only need to pre-compute 1, right? So you can always add up your encryption 1 by many times, right? Until you get, so let's say if you want to encrypt number 7, you simply add up encryption 1 6 times, right? So that should still be much faster, right? According to our profiling results, right? So it's like 100 seconds versus 6 seconds, something like that. But that's, let me see. Okay. I think this is it. Right, and another benefit of doing so is that we can actually leverage the multiple, excuse me, the multiple cores in the hardware, right? So now this is more meaningful. I think I just mentioned something like, doing parallel is not very helpful between the ciphertext and the plaintext, but this is not the same case, right? So this means we can break down the encryption or a single encryption procedure with multiple cores, right? Because now, let's say we try to add up, let's say encryption for 1 6 times, but you can do that in parallel with 2 cores, right? So it's like it looks like a tree here, right? So you do not need to use a single core to do this addition of inc 1, right, 6 times. You can do that with 2 cores. Right? It's like so it's like a tree, right? So. And that's not possible in the original or in the vanilla homomorphic encryption scheme. So this is what we mean by real parallelism. It's not simple data parallelism. So it's computational parallelism. Right? And that's also why we call it parallel caching. Right? So it's both caching and parallel. Right? It's caching in the sense that we can pre-compute some of plain text messages, right? And we can do that in parallel. All of these are for a single encryption, right? So we are working at a finer granularity in this context, or we are digging into a single encryption operation, right? Not that naive parallelism given a large volume of data, right? So it's not a simple data parallelism. It's actually inside a single data operation. So which is more useful. Right. So then again, so we need to ensure 2 fundamental properties, right? Before we talk about the performance. So the correctness is obvious. I hope so. So because of the homomorphic property, and the security is a tough topic to talk about. So I think I will skip that. But the key idea is we want to make sure our construction from pre-computed ciphertext message is not deterministic. So if you do not have a background about security, so I can quickly introduce you to this concept. So in computer security, anything deterministic is not considered as secure. So as long as you have a deterministic ciphertext, then it's not secure. Largely because of a popular attack called frequency analysis. So if you have deterministic ciphertext messages, then your data will at some point be broken. So that's already proven. So and then beyond that, we want to make sure our scheme is performant, right? So and we have some results there, and and if you are interested in this research, feel free to. I do provide the link, but if it's hard to take note of the link, then you can just Google maybe my name. So it's called Siegel Model 23. So you should be able to find out. But I would still affiliate with Nevada, so don't worry about my. So that was me. So that's so okay. I don't think we'll have time to talk about the VectorDB, but maybe let me spend 1 minute to talk about it. Maybe this figure, right? So you probably have heard of. I think maybe many of you have used the large language models, right? So we use that ChatGPT to help you answer some questions, right? But one of the very popular applications or systems built upon LLM is called RAG, or retrieval-augmented generation. So if you look at this figure, right, so on the right-hand side, we have the query result, right? So the input, so this is you. This is you are typing in front of your keyboard, asking some questions on ChatGPT, right? But sometimes ChatGPT can be fine-tuned using your local information, right? So maybe with your own experience, sometimes if you provide more information or more context of a question, then usually GPT can do a better job, right? To answer your question more, for example, accurately or maybe faster, right? So those local information is actually can be extended into a very large but still local database, right? So maybe you're maintaining a let's say maybe 1 terabyte of information for a company, right? And then you want to do some query, you want to ask some question from ChatGPT, then if you do not care, if you're not concerned with the sensitivity of your local data, then you can choose to upload some of your database, your local database information to GPT, right? But then the question becomes, how can you efficiently and effectively retrieve the related information from your local database that is arguably most relevant to your query or to your question, right? So it's really an information retrieval problem, right? So then the state of the art of this area is that let's try to map both your query and your question and your local database tuples, by tuples I mean the data pieces, into the same space, into the same vector space, so that we can easily compare the distance or the similarity between your query vector and the vectors embedded from your local database, right? Because it's easier to calculate the distance, the Euclidean distance in the vector space, right? So then in that sense, vector database is considered as a indexing system to help the user to quickly retrieve or to both quickly and accurately retrieve the relevant information from their local database so that they can combine their query and retrieve the information from the local database to GPT so that the latter can better answer the question. So that's the key idea. And then, this is a very active research area. So there are multiple techniques to accelerate this, vector database mechanism so that, we can quickly retrieve those relevant vectors from the local database, right? So let me stop here. And feel free to come to me if you have any more questions. Thank you, guys.